Hi everyone! In this presentation, our group aims to compare the performance of lightweight LLMs after fine-tuning with GPT-4o on sarcasm classification. Here's a quick overview of what we'll cover. First, we'll start with the project overview and motivation, which is the problem we're addressing and why it matters. Then, we'll look at LLM architectures and fine-tuning methods with a focus on small-scale models. Next is our dataset and pre-processing workflow, outlining how we prepared the data for training. We'll review baseline performance and zero-shot benchmarks to set a comparison point. Then, we'll walk through the fine-tuning process, specifically using LoRa and adapter P. Finally, we'll discuss evaluation metrics and comparative insights, such as how the models performed and what we learned. In this study, we ask a focused question. Can smaller specialized language models rival GPT-4o in understanding sarcasm? Our objective is to evaluate the effectiveness of fine-tuned lightweight models, which is around 3 billion parameters, in sarcasm detection. We also use GPT-4o as a benchmark, allowing us to compare performance and assess whether these compact models can offer competitive understanding with far fewer resources. Now you may ask, why sarcasm? Sarcasm flips the intended meaning of a sentence, making it difficult for language models to interpret accurately. Models often take sarcastic remarks literally, which can lead to misleading results. For example, "Oh, fantastic! Another meeting that could have been an email." A generic model might read this as positive due to the word fantastic, but a fine-tuned model could recognize it as frustration. This matters in real-world applications, such as for sentiment analysis, where the literal meaning is positive, but the true sentiment is negative. Or for toxicity detection, such as, "You're so good at your job," sounds polite, but it's not. Sarcasm detection could even be used to gauge one's mental health, such as, "I'm just thrilled to be alive," may mask emotional distress. These examples show why sarcasm detection is both challenging and essential. This slide outlines our sarcasm detection pipeline. We start with the balanced data from the Sarcasm Corpus v2 and Kaggle News headlines. After baseline evaluation with 7 lightweight LLMs, we select the top 3 models like Tiny Llama, Cerebras, and Phi2 for fine-tuning using LoRa and adapter P. Top 3 performing and weakest models are fine-tuned over 1 to 2 epochs, then evaluated on unseen datasets. Finally, we compare results against baseline models and GPT-4o zero-shot performance to measure gains. In this section, it comprises of a brief overview of the LLM models we chose. Let me introduce Phi2, a compact and capable decoder-only transformer model by Microsoft, featuring 2.7 billion parameters and trained on 1.4 trillion tokens. It uses components like Phi attention for deep self-attention, new GELU-activated MLPs, and rotary embeddings for positional encoding. The architecture is optimized for next word prediction and enhanced through RLHF and instruction tuning. Next, we have Tiny Llama v1.1, an ultra-lightweight decoder-only model developed by STAT, NLP, and SUTD in 2024, designed for efficient deployment in resource-constrained environments. With 1.1 billion parameters, it builds on Meta's Llama architecture and uses Llama-style attention, CELU-activated MLPs, and dual Llama RMS norm for normalization. Its compact 22-layer design maintains performance while significantly reducing computational overhead. Now, let's look at Bloom 3B, a multilingual decoder-only model developed by Big Science in 2022. It features 3 billion parameters and supports inputs across languages and code, making it versatile for global applications. Its architecture integrates fused QKV attention with RDB positional bias, expands features up to 1240 with Bloom MLP, and uses layer norm extensively for stability. Next in our lineup is BTLM 3B8K, a model optimized for long context understanding and efficient extrapolation. Released by Cerebras and OpenTensor in 2023, it features 2.6 billion parameters, an 8K context window, and uses one-dimensional convolution-based attention, and MLP layers with SWIGLU activation. Its architecture also includes RDB positional embeddings and maximal update parameterization scaling for training efficiency. Gwen 2.5, developed by Alibaba Cloud in 2024, is a multilingual model built to handle large-scale generation with an impressive 128K context window and 8K token output. It features 3.1 billion parameters, supports 29 languages, and leverages linear attention projections and CLU-activated gated MLPs. RMS norm is used throughout to maintain stability, making it a powerful choice for extended sequence tasks. Representing a faithful open-source reproduction of Meta's Llama series, OpenLlama v2 offers a streamlined and efficient decoder-only architecture. With 3.4 billion parameters and large 3,200 dimensional embeddings, it features separate projections for Q, K, and V, CLU-activated MLPs, and RMS norm for stability. It is optimized for performance in setups requiring large hidden sizes without sacrificing efficiency. Finally, we have DeepSeek R1 Distilled Llama 8B, the only 8 billion model in our selection, and uniquely enhanced through reinforcement learning without supervised fine-tuning. Distilled from DeepSeek R1, it features Llama-style attention, CLU-activated MLPs, and RMS norm for stable, long-form generation. This model was chosen as a performance benchmark to assess the impact of RL and larger model size against the 3 billion models. In this section, we'll walk you through the datasets we chose to work with and explain how we prepared this data before diving into our analysis. Our University of California, San Diego fine-tuning dataset includes around 28,000 news headlines, where around 14,000 sarcastic headlines are from The Onion and around 15,000 non-sarcastic ones are from HuffPost. Why this dataset works well is that it has strong sarcasm signals. The Onion's headlines provide clear satirical examples that language models typically struggle with. This dataset also has clear contrast, where the HuffPost's factual reporting creates the perfect counterpoint for classification. Next, it is self-contained, where each headline requires no additional context, making training more efficient. Now, let's turn to our validation set. For testing the performance of our model, we are using the Sarcasm Corpus v2 from the University of California, Santa Cruz. What makes this dataset special? It breaks sarcasm into 3 distinct flavors. First, we have general sarcasm, with 3,260 examples per class. Think of phrases like, "Oh, that's just perfect," when everything is clearly going wrong. Then, there's hyperbolic sarcasm, with 580 examples per class. You know the sentence, "I've told you a million times," when it's really been just a few times? And finally, rhetorical questions, with 851 examples per class. These are questions not meant to be answered, like, "Could you be any more obvious?" Yes, think about Chandler from Friends. Why do we value this dataset? It gives us balanced classes, diverse sarcasm types, and pulls from real internet arguments. So we're testing against authentic human snarks, not artificial examples. Now, let's talk about how we prepared our data, a step that really makes or breaks model performance. We took a 4-step approach here. First, we resized our datasets, cutting down to 10,000 training examples to keep things manageable, while choosing 200 samples from each sarcasm type for a fair evaluation. For tokenization, we converted our text into tokens with proper padding and consistent lengths, which helps fine-tuning run smoothly without those frustrating crashes mid-process. We also standardized our data, with clear labelings such as sarcastic sentences as yes and non-sarcastic ones as no, giving our model unambiguous categories to work with. Finally, we balanced our datasets to get a perfect 50-50 split, preventing our model from cheating by predicting the more common class. After all, we wanted to detect actual sarcasm patterns, not just playing the odds. With our data properly prepped, ready to see what our baseline results look like? In this section, we'll talk about the evaluation metrics and the benchmark performance. To benchmark the 7 baseline models that we have chosen for evaluation, we used 4 key metrics: accuracy, precision, recall, and F1 score, where each provides different insights into the model's behavior. This slide and the following slide are the result of the baseline models before fine-tuning. Let's take a look at the result for generic sarcasm 200 test set. First, we observed that Cerebras achieved the highest accuracy of 0.555, closely followed by Tiny Llama, which scored an accuracy of 0.55. If we look at the F1 score, Tiny Llama actually performed better with an average F1 of 0.5480. Next, we present the baseline results on the hyperbole test set. Compared to the generic test set, all models showed a noticeable drop in overall performance, especially in terms of balance between sarcastic and non-sarcastic classification. First, Phi2 stands out with the highest accuracy as well as the highest average precision and a balanced recall. Among all models, DeepSeek R1 Distill Llama 8B was the most stable performer, delivering relatively balanced scores and the highest average F1 score. Next, we present the baseline results on the rhetorical test set. Overall, we observed that most models struggled to interpret the implied meanings in rhetorical questions, often leading to biased predictions towards one class. First, Phi2 once again delivered the strongest performance, with the highest accuracy, precision, and recall. In terms of F1 score, Cerebras did the best. These models consistently delivered competitive and balanced performance across accuracy, precision, recall, and F1 score, demonstrating strong generalization to both straightforward and nuanced sarcastic expressions. Tiny Llama showed high F1 scores and accuracy, especially in the generic sarcasm and rhetorical questions. Phi2 consistently achieved the highest or near highest precision and recall for sarcastic content, indicating strong capability in detecting subtle sarcasm. Cerebras demonstrated solid accuracy and precision across tasks, making it a stable candidate. In contrast, Gwen 2.5 had the lowest performance across all three datasets, with particularly low recall and F1 scores. We included it intentionally in the fine-tuning stage to examine whether a weak-performing baseline model could substantially improve with task-specific fine-tuning. This selection strategy allows us to explore both top-performing models and a worst-case baseline, providing a well-rounded evaluation of fine-tuning effectiveness. With the baseline results of all models on the test sets, namely generic sarcasm, hyperbole, and rhetorical questions, we will proceed with fine-tuning the models. In this section, we will explain our process of fine-tuning. We used a causal language model training objective, which preserves the model's next token prediction abilities while allowing us to adapt to our specific domain without losing its general capabilities. We then employed two key fine-tuning techniques. The first is LoRa, which injects trainable low-rank matrices into frozen model layers. This is particularly efficient and ideal for fine-tuning large language models with limited computing resources. The second is Adapter P, which adds lightweight bottleneck layers with residual connections to the transformer architecture, making it especially efficient for nuanced tasks like sarcasm detection. We also experimented with two epoch configurations, which are single epoch runs for quick adaptation and two epoch runs to provide more exposure to our dataset and potentially deeper learning. For the fine-tuning, we used those 10,000 examples from the University of California, San Diego News Headlines dataset that we mentioned earlier. Now, let's move on to evaluating our fine-tuned models and see how they perform. In this section, we'll be analyzing the results by highlighting the top 4 model, fine-tuning method, and epoch combinations that achieved the highest accuracy. For the performance of fine-tuned lightweight models on a generic sarcasm in the Sarcasm Corpus V2 dataset, Gwen saw the greatest improvement of 2.29 times from its baseline accuracy result. This shows the potential of models which did badly at baseline can improve more than other models which did better at baseline after fine-tuning. This demonstrates the performance gains that fine-tuning can bring. Gwen LoRa fine-tuning with one epoch achieved the highest accuracy and F1 score among all fine-tuned lightweight models. That, however, is unable to beat GPT-4o, showing that GPT-4o still has better generalization than Gwen after fine-tuning. From the table, we see that Gwen after one epoch of LoRa fine-tuning has the best accuracy, recall, and F1 score, even though it has the worst performing baseline model. Cerebras after 2 epochs of LoRa fine-tuning has the best precision for sarcasm detection. This could be because Cerebras is more cautious at flagging sarcasm, making it having the highest precision. Moving on to the performance of fine-tuned lightweight models on hyperbole sarcasm, Phi2 after LoRa fine-tuning of one epoch achieved the highest F1 score. All models have improved over their baseline scores, with Cerebras improving 41% for its accuracy. From the table, we see that Phi2 LoRa fine-tuning for one epoch has the highest F1 score and accuracy of 0.62, and Phi2 adapter P fine-tuning of 2 epochs has the highest recall, with the same accuracy score of 0.62 as well. This means that LoRa fine-tuning of one epoch gives a better trade-off between recall and precision, whereas adapter P fine-tuning of 2 epochs caught more actual hyperbolic sarcasm cases. Phi2 adapter P after one epoch of fine-tuning gave the highest precision, meaning that it is the most careful at flagging hyperbolic sarcasm correctly. For the rhetorical question sarcasm, fine-tuning significantly improved both accuracy and F1 score for most models. For Gwen with LoRa fine-tuning of one epoch, it showed the most dramatic improvement of 1.71 times from its baseline accuracy score. This shows that LoRa fine-tuning helped Gwen handle rhetorical questions far better than before. Despite the two tiny llama models achieving high accuracy scores, their F1 scores were a lot lower. This is due to their low recall values, meaning that the models frequently failed to identify rhetorical question sarcasms. Looking at the table, tiny llama adapter P after one epoch of fine-tuning has the best accuracy score. Phi2 adapter P after one epoch of fine-tuning gives the best F1 score, even though Gwen LoRa after one epoch of fine-tuning gives the best precision and recall. This suggests that Phi2 adapter P strikes a more balanced trade-off between precision and recall, while Gwen LoRa might be more confident but possibly overpredicts or underpredicts in some cases, affecting the F1 score. Next, we evaluate the fine-tuned models on unseen questions from the Kaggle headlines dataset, which is the same dataset we used during fine-tuning. Cerebras, after just 2 epochs of LoRa-based fine-tuning, achieved the highest scores across the board, with an accuracy of 0.985 and an F1 score of 0.982. Interestingly, Gwen also performed very consistently after LoRa fine-tuning. Whether trained for 1 or 2 epochs, it reached accuracy and F1 scores of 0.95, which is impressive for a lightweight model. In contrast, GPT-4o, which had previously delivered strong results on other tasks, underperformed on this focused headline classification task. One possible reason for this could be the differences in writing styles between the datasets. The Kaggle headlines used for fine-tuning are the formal and structured newspaper headlines, while the Sarcasm corpus v2, used for evaluation, consists of informal dialogues, full of slang and expressive punctuation. Lightweight models that are specifically fine-tuned on these structured formal headlines were better to adapt to that style, while GPT-4o, having been pre-trained on a broader mix of internet and social media text, might be more tuned to informal language and less optimized for the structure of news headlines. What this tells us is that domain-specific fine-tuning really matters. It can dramatically boost performance, even to the point of outperforming GPT-4o in specialized tasks. It is worth noting that Gwen, which initially performed poorly at baseline, showed the greatest improvement after fine-tuning. This is a reminder that models that start off weaker can still catch up or even overtake others with the right fine-tuning. In fact, Gwen with LoRa fine-tuning for just one epoch achieved the best results among all lightweight models on the generic sarcasm questions. However, it still didn't surpass GPT-4o, showing that GPT-4o continues to lead in generalization capability, even if it can be outperformed in narrow, fine-tuned settings. From the table, we see that Cerebras after 2 epochs of LoRa fine-tuning gives the best accuracy, precision, recall, and F1 score for the unseen questions from the same dataset it is fine-tuned on. This indicates strong within-domain generalization and effective learning of the dataset's writing style. Let me highlight our key findings on the lightweight language models. Lightweight LLMs like Phi2, Tiny Llama, and Cerebras showed impressive improvements after fine-tuning, especially using LoRa and Adapter P. While GPT-4o excels at zero-shot tasks, fine-tuned smaller models often outperformed it for specialized tasks. Phi2 with Adapter P consistently handled sarcasm best, particularly in rhetorical questions and hyperbole sarcasms. Among all models tested, Cerebras delivered the most stable and balanced performance across all metrics. These results demonstrate that fine-tuned smaller models can be highly effective for specific applications. As we come to the conclusion of our presentation, we would like to address some important limitations of our study and outline potential improvements for future work. Regarding limitations, we worked with a relatively small validation dataset of 200 examples per class, which may restrict the generalization of our findings. We should consider this when interpreting results. Additionally, due to compute constraints, we were only able to explore a subset of LLMs and fine-tuning methods, leaving other potential valuable approaches unexplored. Some improvements that we can have to our study is to expand our research to other LoRa variants, specifically QLoRa and AdaLoRa, while also increasing the number of training epochs. We believe that testing zero-shot chain-of-thought prompting and in-context learning approaches can potentially improve performance without the computational demands of full fine-tuning. Thank you!